Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to just do a few review problems related to orthogonal matrix stuff. And so I just want to start off, and I think I said this at one point in another video, but we never really proved it or got into like why that is, but I want to kind of give an argument for why in it, like a generic 2x2 orthogonal matrix is going to either be a rotation or a reflection. And it definitely has kind of everything to do with a unit circle. So the idea here is like if we take, so an orthogonal matrix, right, is one where QTQ equals the identity, right? And so I'm just going to kind of use that idea. And so if I have like A, C, B, D, let's say, so that's my QT of A, B, C, D, right? And I multiply it, it should be equal to the identity if it's orthogonal, right? And so if you look at what that says, if you just like do out the multiplication, right, you would get that A squared plus B squared is the first top left corner, and then you would get AB plus CD here, and then you would get AB plus CD down, CD down here, and then you would get B squared plus D squared here. So this thing has to equal 1, 0, 0, 1. And so you can see, you know, like that A squared plus B squared has to equal 1, and B squared plus D squared equals to 1. And so if that's the case, basically, like, let's actually color code this a little bit more here. So let's say that one and that one. So if A squared plus B squared is equal to 1, then your vector AB, right, could basically be identified as A equals cosine theta, right, and B equals sine theta, because then A squared plus B squared is equal to 1, right? And down here, if you have B squared plus D squared equals 1, then BD, that vector, you'd get a similar thing. B could be something like cosine of a different angle, let's say like phi, and then D could be sine of some other angle like phi. And then we have these other identifications, right? We have that like AB is 0, AB plus CD is equal 0, and that's the same thing like here too. So, so that one, you know, we'll only get like one more extra thing there. So if AB plus CD, well, here, let's just for space reasons. So if AB plus CD equals 0, then that's basically saying that cosine theta times cosine phi plus sine theta sine phi equals cosine, or well, equals 0, right? But this thing is a famous trig identity. That's like the difference identity for cosine. So that's the same thing as cosine of theta minus phi equaling 0. So if you think about what this is saying, basically it says that, you know, in order for that to be true, theta and phi need to be pi over 2 off, right? Like literally if you just did like cosine of like any angle you want minus an angle that's pi over 2 further down. So, so if these need to be like pi over 2 off, you can just find a function that is shifted pi over 2 from, like, say, cosine of theta up here, and that function could be sine, right? Sine and cosine are off by pi over 2. So basically what I'm saying is that you can take, instead of working with cosine of phi, you can let b equal sine of theta, okay? And so what you're sort of getting now is everything just in terms of theta, and so you would need to shift this also to be pi over 2 off. So it turns into like cosine because it was sine before, and now you need to shift it back to cosine. or shifted to cosine. So what you're basically getting is, if you go back to this AB plus CD equals 0 kind of identification too, we're seeing that like if B equals C, right, then A equals minus D, right? And in that case, you would have, so let's see, so B equals C. So we're just doing everything in terms of theta here. So we have sine theta, that's B equals C. Then you would basically need A to be cosine, right? And then D, you need to have negative D, so that's negative cosine theta. And then another case here is if you do, like from this identity also, if B equals negative C, right, then, then you're getting A times negative C plus C D, right? And then take a C out, right? You get D minus A equals 0. And so here, just A needs to equal D, right? And so in that case, the matrix you get is A equals D, so you get cosine in the top left and cosine in the bottom right. And then B and C are off by a negative. So you have sine here, and then minus sine here. And, hopefully, just because we've seen it before, you know that this one is this is your rotation matrix. And this one is a reflection matrix, okay? Basically, I feel like we've seen this one quite a bit, but this one maybe we haven't seen it as much. The way I kind of think about this, I'm going to have to erase some of this. If you think about it in terms of like where the basis vectors land, right? So you've got like, here, let me draw a circle. So you've got like E1 is like your standard basis vector, and then E2 is your other standard basis vector, right? So, this, this column right here just says that E1 is going to go to like somewhere on the unit circle, like right here. So this one is like the transformation on E1, basically, right? You land there. So what we're basically going to get is you're going to see a reflection over this. And then this is, so saying that if you go the sine of theta in the x, so this was, this y is the sine of theta. So I go that much in the x, and then I go minus cosine theta. So cosine theta was the x distance, like this x distance, right? So if I go over that much in the y, this much in the y, and then down the x distance, this vector is basically the transformation of E2. And so it's probably not perfect, but you can see that like this is symmetric with that, and this is symmetric with this, like across that line of reflection. So, and I just picked like a random theta, but you could fix it to anything you want, and you would be able to see it. So, so that's kind of like a rough sketch of the proof of this thing. So, and I could do the same thing here that I did up here for this, but I feel like we've seen that one before to see why that's a rotation. All right, so for this problem, I just want to prove that if Q is orthogonal, and we've got this set of vectors, V1 through Vk is an orthonormal set, then basically Q applied to all of those is also an orthonormal set. And so basically it just uses like some of the important properties of orthogonal matrices. So we know that like if Q is orthogonal, then that's equivalent to the magnitude of qx equals the magnitude of like that a vector x, and that's also equivalent to qx dotted with qy equals x dotted with y. And so we need to show two things, right? We need to show one that like these vectors in here are length 1, and that basically if you dotted any two of them, then they would be either 1 or 0, right? 1 if they're the same vector, and 0 if they are different vectors. So, so basically it just comes out of these properties right here. So we know that the magnitude of any of these vectors, like v sub I, is equal to 1, and, well, I'll say, and since magnitude of like q times any vector x equals the magnitude of x, given an orthogonal matrix, we get that basically magnitude of q v sub I equals 1 for all I, right? And so that does like one property of an orthonormal set. It proves that these things are all length 1, no matter what index I got there. And then so that uses sort of this equivalent property to orthogonal matrices. Now I'm basically going to use this for the other one. So for that one, we can just say like this: since Q is orthogonal, right, we know Q. I'm going to need a new line. QX. Nope, not x anymore. I want to do like Q v sub I dotted with Q v sub j is equal to v sub I dotted with v sub j. And then since that set v1 through vk is orthonormal, we know that v sub I dotted with v sub j is basically equal to 1 if I equals j, and then 0 if I doesn't equal j, right? These are my brackets. I still can't make brackets after all these years of math. And that does it, right? So we have shown that set Q V1 through VK is orthonormal. All right, so another really important thing from this unit is these kind of problems where you build like a symmetric matrix that has certain eigenvalues and like eigenspaces, and it relies on that spectral theorem, which basically says that if you can orthogonally diagonalize a matrix, that matrix is like a symmetric matrix. And to do this, we also need the spectral decomposition thing, where we basically have like an eigenvalue times like Q1, we'll say, and then Q1 transpose plus an eigenvalue, Q2 transpose, right? And like you can just keep doing that. And this whole thing is what will equal like our symmetric matrix. So we basically need to get these vectors Q, and Q sub I is the basically like orthogonal or ortho. Q sub I is like the orthonormal vectors, right, that make up like the matrix capital Q. It is like the orthogonal matrix. So, so this one's a little trickier because you can see like, so for the eigenspace of like, I guess lambda 3 here, you know, if you dot this with these guys, so 1 times 1 minus 1 is 0, right? And then 1 times 1 minus 1 plus 0. So this is perpendicular to these two, which is good. So we can just keep that the same. That can basically be, well, more or less like one of my Q vectors, but it's not length 1, right? So I'll have to make it length 1 too. But these ones are not perpendicular, right? These span some sort of plane, but in R3. But if you just dot these, like you get 1 plus 1, you get 2. You don't get 0. So we actually have to do more work here because we kind of have to do some Gram Schmidt kind of stuff to get a orthonormal, well, mostly an orthogonal basis for this space. And then we'll normalize everything. Then we'll have this structure and we can finally get our matrix. So that's a lot of work, but that is kind of the plan here. So, I'm going to call this just, I don't know, V1, V2, V3, all right? And when we do Gram Schmidt, you know, we can leave one of these vectors the same. So I'm just going to say V1 equaling the vector 1, 1, 0 is like the one that I want to just kind of keep the same. And then I'm going to make V2 perpendicular to V1, but it'll still be in the span of like E1, the eigenspace for lambda 1 or 2 there. So, you know, to do Gram Schmidt, basically this other vector that I'm going to build in my set, I'm just going to call it, I don't know, U, is just going to equal V1, and then minus the projection of, which one? So of V2, sorry, onto V1, right? And that would do it. That's like what we do for Gram Schmidt. And if you wanted to do, if you had more vectors, you would just do more and more subtractions that are these projections. So if we do that, U is going to equal 1, 1, 1. Oh, no, sorry. I just looked above, and I want this to be V2. Sorry. So I take this vector, right, that thing, minus the projection of V2 onto V1. So it's going to be like 1 plus 1 plus 0 over 1 squared plus 1 squared plus 0 squared, and then times 1, 1, 0. And so if you do that out, you'll get the vector 0, 0, 1. And so now the set, so E1, I'll just say it like this. Let's do some different colors there. So E1 is still equal to the span of V1 and U, okay? But the nice thing is that 0, 0, 1 is perpendicular to 1, 1, 0, right? Definitely you can see that when you dot those. But it's also going to be perpendicular to this. So 0, you know, you can see it, right? And so now we have a fully perpendicular set. Now we just got to normalize them. This one's actually length 1 already, which is nice. So we can use that little hat notation. And so U1 is actually a unit vector. But that's just a coincidence. And so we would need, so Q1, let's say, is just equal to V1 over the magnitude of V1. And so that's going to be 1 over root 2, 1 over root 2, 0. And then Q2 is, let's say, now we'll call it Q3, is V3 over the magnitude of V3. So that's going to be the same thing, but with a negative, right? So we get negative 1 over root 2 and then 0. And so now we have it. So A, the matrix I'm looking for, is going to be equal to like lambda 1, which is like 1, times q1, which is 1 over root 2, 1 over root 2, 0, times q1 transpose. So 1 over root 2, 1 over root 2, 0. And then plus 1 times 0, 0, 1, my u vector, times u transpose, 0, 0, 1. And then plus, where is it? Negative 2 times q3, sorry, which is 1 over root 2, negative 1 over root 2, and 0, times the transpose, 1 over root 2, negative 1 over root 2, 0. And I need to erase some things because I don't have room. So I'm going to erase all of this really quickly. These problems are very long and tedious. So if you do all that out, it's a lot of multiplication. Again, you're doing like you're going to get like a 3 by 3 in here, a 3 by 3 in here, and a 3 by 3 in here. This one you can kind of see is just going to be literally 0, 0, 0, 0, 0, 0, and then 0, 0, 1. So that one's kind of nice. But some of these other ones you got to be kind of careful, and especially this one. I would maybe multiply the negative 2 in and then multiply the vectors. Any way you do it, though, you're going to get negative 1 half, 3 halves, 0, 3 halves, negative 1 half, 0, 0, 0, 1. And this matrix, if you look, first off, notice it is symmetric, right? It's got symmetry along the diagonal. And like literally, if you compute the eigenvalues of this, you're going to get this stuff. You're going to get 1 with multiplicity 1 or 2, and negative 2 with multiplicity 1. And the eigenspaces would match up with this. So it's a very, very, very useful trick to be able to build certain matrices that have certain properties associated with their eigen stuff. And it uses a lot of theory there to get to that point. But that is it. So that matrix does what we wanted it to do. All right, just one more problem I want to kind of review. Another just kind of important property is this with orthogonal things is that like we can sort of decompose vectors in terms of like an orthonormal basis, okay? And the way I literally always think of this is like if, we'll just call it like alpha, if I have some vector alpha, right? That is, let's do like a more interesting one. We'll go 1, 2, 1. So alpha is the vector 2, 1, right? But I can think of the vector 2, 1 as equal to the projection of alpha onto I hat. And then I can add to that the projection of alpha onto j hat, right? Because what I basically could do is I could think of it as 0, 0, 2. That's just very wrong. I don't know what I was thinking there for saying 2, 0. And then add, that's the projection here, right? Add to that 0, 1, and that's the projection here. And so we're basically doing the same kind of thing. And so this is, actually, you can even write this if you want. You could call this description of alpha, you could write a little b here, and you could say b is like the basis that's defined by the span of like the standard basis vectors E1 and E2. But here, what I'm going to do is I'm going to define 1, 1, 1, which is like a base or a vector with the standard basis in terms of another basis. So 1 defined by U1, U2, and U3, which are all orthogonal. So we're going to do the same kind of thing. Basically just we're going to write V, and this is like the correct notation. I'm just going to call B2 because I have B1, let's say, up there. So basis 2 is the set U1, U2, U3. And it's just going to equal the projection of V onto U1 plus the projection of V onto U2 plus the projection of V onto U3. And if you do all that out, just a lot of computation, honestly, you would get this. And so, yeah, you just crank through all those projections. And so what you want to think of here is like this vector is basically telling you how much of these basis vectors you need to get the equivalent of like a 1, 1, 1, right? Here you can think of this as 1 E1 plus 1 E2 plus 1 E3. If you add those together, right, you'll get 1, 1, 1. And there's lots of things like this in the real world where you need a different basis set to describe something. And I think I talked about how, like, I have one friend who works in materials science, and he uses linear algebra all the time because his crystal structures that he works with don't do well with like the standard basis. So what he does is he takes vectors like this, and it's a much more straightforward computation thing on a computer. But he basically can just do these change of basis sort of things like we're doing, and write a vector like V here, let's say, in terms of basis 2, which is just defined as, in this case, these projections. But the projection thing is a nice case for specifically perpendicular basis vectors. So, it works the same way with E1 and E2 because E1 is perpendicular to E2, much like, U1, U2, and U3 are all perpendicular. So that's it.